Hi everybody, thank you for tuning in. It's Rodri Davis here, and I thought I'd provide an update on the Geodynamic Adjoint Optimization Platform, which is a platform that's been largely funded by the Australian Research Data Commons, but also has significant support from Auscope, the NCI and Geoscience Australia. Okay, so first of all, what is it? So on the top left hand side here, you can see an outline of the data sets available to constrain the mantle's evolution. Now the size and spacing of the points reflect the data availability, and these decrease with depth and age. Now in isolation, each of these data sets allows us to probe the mantle at a range of spatiotemporal scales, but when combined they actually constrain the mantle's evolutionary pathway. The challenge lies in fusing these datasets through inverse geodynamics and high-performance computing to reconstruct the mantle's evolution and its impact at Earth's surface. So to summarise that challenge more concisely, what we want to do as a community is move from idealised forward models to data-driven simulations that rigorously account for observational constraints and their uncertainties. And to do this, we need an inverse approach. Now, the approach advocated through the GeoDOP project is to use adjoint-based screens, which exploit gradient information and allow us to reduce the misfit between a model prediction and an observation. The bottleneck to this type of work thus far has been the fact that the development of adjoint models for nonlinear time-dependent problems is notoriously difficult. Now, GeoDOP aims to overcome this substantial practical challenge and provide efficient and portable adjoint-based research software infrastructure, which will allow the community to tackle fundamental research questions via data-driven simulations. So how do we hope to do this? Essentially by further developing and integrating 3 state-of-the-art research software libraries from the global research community. So the first one is FireDrake, which is an automated system for solving variational problems using the finite element method. And we use this essentially to run our forward models, and you'll see why it's quite neat shortly. The second library is Dolphin Adjoint, and that automatically derives the corresponding adjoint equation for any forward model in a form compatible with FireDrake. With the forward models and the adjoint equations, we're then going to use the Rapid Optimization Library, which provides a framework for rapid, large-scale optimization and has been integrated with Dolphin Adjoint or PyAdjoint. The focus of this talk will be on FireDrake, but the 3 packages are really integral to the GeoDOP project, and as we move forward in time, we'll obviously start to integrate the other 2. Okay, so FireDrake, as I said, it's an automated system for solution of partial differential equations via the finite element method. Now, the finite element method is highly amenable to automatic code generation techniques because a weak formulation of the relevant partial differential equations, a mesh, boundary conditions, and appropriate function spaces is actually sufficient to characterize the problem completely, as you will see in some of the examples I will shortly go through. FireDrake provides a means to create flexible, efficient, scalable, transparent, reproducible and easily extensible research software, and it has a number of key features that allow it to do so. Okay, the first and one of the key ones is the fact that you can express any partial differential equation using the unified form language from the Phoenix project, and you'll see some examples of this shortly. It automatically assembles the finite element systems, both for linear and non-linear problems. And it allows for sophisticated programmable solvers, facilitated by seamless coupling with PETSI. It also allows for customizable preconditioners, which are very important for a number of classes of problems. FireDrake supports unstructured, structured, and layered meshes, and there is work ongoing to make it support adaptive meshes. It supports a wide range of finite element spaces, both continuous, discontinuous, and some of the more funky element types that are being used more and more in the community. And because it treats finite element problems as a composition of several abstract processes, it allows for sophisticated performance optimizations, which are just beyond the realms of possibility of those that are coded by hand. Further information on the Firedrake project can be found on that website. Now it's generally applicable, and as I said, can be applied to any partial differential equation that can be solved by the finite element method, but our interest is in geodynamics, and the remainder of this talk will focus on those geodynamical applications. Okay, so I'll next take you through some examples highlighting the power of Firedrake. We start with incompressible isoviscous convection in a two-dimensional enclosed domain, which is heated at the base and cooled from the top. Now, solutions to this problem are obtained by solving the Stokes equations for velocity and pressure, alongside the energy equation for temperature and a suitable equation of state. So how does this look in Firedrake? Well, we've set up this problem using a bilinear quadrilateral element pair, so Q2, Q1 for velocity and pressure, with Q2 elements for temperature. Now, Firedrake code is written in Python, so the first step is to import the Firedrake module. Okay, we next need a mesh, and for simple domains such as the unit square, Firedrake provides built-in meshing functions. So we define the mesh here with 40 elements in x and y directions. We next need function spaces, test functions, and functions to hold the solutions. Okay, after which we can specify the important constants of the problems and initialize our initial conditions. It's at this stage where we can define the variational problem using UFL. So as a reminder, this is how the governing equations for geodynamical problems look in their weak form, and this is them in UFL. So the resemblance between the UFL and the mathematical formulation here is clear. Okay, if we focus on the continuity equation, because it's the smallest, you have the grad W dotted with U and integrated over the domain. Okay, so again, the resemblance here is very, very clear. Okay, once we've defined that variational problem, we can set up velocity and temperature boundary conditions. We can configure the output and certain diagnostics if required. We set up the problem and the solver objects, noting that in this case we're using the default options, and then we initialize the time loop and the solve. Okay, so in less than 60 lines of Python, we have a code that allows us to compare our diagnostics to the benchmark solutions, and you can see quite clearly that as mesh resolution increases, we converge towards the benchmark solutions here, the red dashed lines. Okay, so that problem is obviously very simple, but one of the joys of Firedrake is that you can very quickly change the physical approximations and the geometries by changing only a few lines of code. Okay, now I don't have enough time to go through these examples in detail, but we validated Firedrake for simulations of a viscoplastic rheology, where you have a linear temperature and depth dependent viscosity, a plastic viscosity combined through a harmonic mean. So you can see it's very straightforward to incorporate that in our Python and to update the solver dictionaries to account for those non-linearities. We can see once again with these more complex rheological problems, we match the benchmark solutions very nicely, and the changes are minimal compared to that basic example that I showed you previously. You can also look at compressible cases where you obviously update the constants, add new constants, and the reference state applicable for the anelastic liquid approximation. You also update the governing equations in this case, and the main difference is obviously being the stress tensor being updated to account for the non-zero velocity divergence. The Stokes equations are modified to account for dynamic pressure's influence on buoyancy, and the mass conservation equation is modified to include the depth-dependent reference density. You can also see the energy equation being updated here to incorporate adiabatic and viscous heating terms. Now, these are very small changes to the Python and the UFL, but again they allow us to capture more realistic physical approximations with ease. We can also jump into different geometries very easily. So I'm showing you a 3D Cartesian case here, where the only changes required are the generation of the initial mesh, which we generate by extruding a 2D rectangular mesh here, and specification of the solver parameters. In 3D, obviously, the direct solves become computationally intractable, so we use PETSC's field split functionality and the shear complement solve options here to specify our options. Again, we match the benchmark solutions for those 3D cases, And we can also do the same in a 3D spherical geometry, both for isoviscous and temperature dependent simulations, comparing to the benchmark results of Zong. Okay. So where are we now? I'm hoping that I've convinced you that for our forward models, the accuracy and efficiency has been confirmed. We've also demonstrated Firedrake's flexibility via straightforward application to different physical and geometrical scenarios. I haven't shown you these results, but we've demonstrated the scalability on up to more than 12,000 cores on the Gaudi supercomputer. And given the importance of reproducibility in the computational geosciences, I also wanted to point out that Firedrake offers traceable provenance of input data and model configuration in full compliance with the FAIR principles. We've ported, validated, optimized and tested Firedrake on Gaudi, and soon, hopefully early next year, we'll have the module load Firedrake functionality. We've integrated it with gplates, which was actually very straightforward through the Pi gplates interface. And this now allows us really to use Firedrake for addressing research problems from the very frontiers of global mantle dynamics research. It's a really exciting tool that I'm hoping the community will now start to use. We plan to hold a workshop for interested practitioners at the ANU, either in late Q1 or early Q2 2020. We're on the verge of submitting this publication to Geoscientific Model Development, and I'd urge you to read and provide feedback if you can. Where are we going? Well, obviously I didn't say much about Dolphin Adjoint and ROL, but we're really heading down the inverse geodynamic framework, using Dolphin Adjoint to automatically derive the discrete adjoint models from our forward models. Okay, the short story here is that with Dolphin Adjoint, we can change the forward model, its physics or its geometry, and we can get the adjoint with all of the coupling terms for free. Okay, and this removes the major practical challenge that has limited progress in this area to date. We can then use this to optimize, in our case, for unknown initial conditions, given observations of the present day state. And here's a proof of concept from an idealized 2D case showing that we've got much of that framework already working. So we have a reference initial condition, a reference end state, and we optimize for this unknown initial condition through the rapid optimization library. And you can see quite nicely that we recover that initial condition both visually, and we can reduce the misfit in our initial and our final state. So these are exciting times. There's a lot of work left to do, but I think in the 4 or 5 months that this project has been going, we've made some great progress, and hopefully that'll continue over the next few years. Thank you for your time.